Hello, welcome. Welcome to Rank High online classes. Today I am super excited to have you here. Excited about amazing conversations that we have lined up for you. In today's lecture, I am going to discuss a very interesting characteristics of microscopic particles, that is wave particle duality, which was first introduced by a French graduate, de Broglie, a century ago. Apart from the conceptual part, I have added some handpicked mathematics on this topic to help growing your confidence to secure top ranks in engineering and medical entrance examinations. So guys, let's start. Niels Bohr received the 1922 Nobel Prize in Physics for his hydrogen atom theory, based on an assumption of quantization of angular momentum. In the years till 1925, attempts were made to apply the Bohr's theory to atoms with more than one electron and to molecules. However, all attempts to derive the spectra of such systems using extensions of the Bohr theory failed. It gradually became clear that there was a fundamental error in the Bohr's theory. Between the introduction of Bohr theory and the development of quantum mechanics, there were very little new contributions to the understanding of matter, except for an important idea put forth by Louis de Broglie, a graduate student at the University of Paris, who was trying to find a physical justification of Bohr's hypothesis of quantization. Scientists have always had trouble describing the nature of light. In many experiments, light shows a definite wave-like character, but in many others, light seems to behave as a stream of photons. The dispersion of white light into its spectrum by a prism is an example of the first type of experiment, and the photoelectric effect is an example of the second. Photons have momentum was hinted at experimentally only 1 year before de Broglie, when Compton announced in his Compton effect the exchange of energy and momentum of X-rays upon deflection of graphite. Because light appears wave-like in some instances and particle-like in others, this disparity is referred to as the wave-particle duality of light. In 1924, de Broglie reasoned that if light can display this wave-particle duality, then matter, which certainly appears particle-like, might also display wave-like properties under certain conditions. This proposal is rather strange at first, but it does suggest a nice symmetry in nature. Now we will see how can we correlate the energy of photons. De Broglie obtained an equation for the wavelength to be associated with material particle by reasoning an analogy with photons. From quantum theory, the energy of photon E equals h nu. From Einstein's special theory of relativity, which gives the energy of photon as E equals mc square, where h is the Planck's constant, nu is the frequency, m is the rest mass of a photon, and c is the speed of light. Equating these two expressions, we get h nu equals mc square. Now we will derive the de Broglie wavelength from the above expressions. Since c equal to lambda nu, that is the speed of light equals its frequency times its wavelength, we can substitute for the frequency, and after rearranging we get mc square equals hc by lambda. Cancelling c out of both sides and realizing that mass times velocity is the momentum, that is p, we can rearrange lambda equals h by mc equals h by p. De Broglie extended this relation into the dynamics of a particle and proposed that a wavelength lambda is associated with a particle in motion, for which the momentum equals mass times velocity p equal to mv. Thus, the Broglie wavelength for particles can be written as lambda equals h by mv equals h by p. Now we will explain that the Broglie wavelength with some illustrations. The wavelength lambda, which is a wave property, is associated with the velocity, which is a particle property, of a particle of finite rest mass m by Planck's constant h. For macroscopic particles, the de Broglie wavelength is so short that it does not lead to observable phenomena. However, for electrons, neutrons and other microscopic particles, the wavelengths may be of the order of interatomic distances in solids. Consider two examples that illustrate the importance of the Broglie equation. First, if a baseball having a mass of 150 grams traveling with a velocity of 150 kilometers per hour, the de Broglie wavelength will be lambda equals 1.06 multiplied by 10 to the power minus 34 meter. Such an immeasurably minute wavelength is undetectable even under modern conditions and of no practical consequence. The reason is the large value of m. What if we calculate the Broglie wavelength of an electron instead of a baseball? In the second example, there is an electron which is much smaller than a baseball. Since the Broglie wavelength is inversely proportional to mass, we would expect that the Broglie wavelength of a particle gets larger as the particle gets smaller. For an electron moving at the same speed as the baseball, the Broglie wavelength is lambda equals 1.75 multiplied by 10 to the power minus 5 meter, which is 17.5 microns. This wavelength corresponds to the infrared region of light. Electrons typically move at higher speeds than this, and the Broglie wavelengths are typically shorter in the range equivalent to X-rays, which in fact can be diffracted by crystals. Now we will see how scientists justified the Broglies hypothesis. It was recognized that the Broglies hypothesis could be tested by scattering a beam of electrons from a crystalline solid as a way of getting a grating of suitable dimensions to match the wavelength of electrons of accessible energies. In 1927, Clinton-Joseph division just did that. After accidentally breaking a vacuum tube with a nickel sample in it, division reconditioned the nickel sample by heating it and formed large nickel crystals. Aware of the Broglies ideas, division with co-worker Lester Gamma exposed a nickel crystal to electrons and found a diffraction pattern exactly as one would expect if electrons were indeed waves. This diffraction of particles showed that particles did have wave-like properties as predicted by the Broglie. Additional work confirming the wave nature of electrons was performed later in that year by G.P. Thomson, the son of J.J. Thomson. Similar diffraction effects have been observed with neutrons, protons, helium atoms and hydrogen molecules, indicating that the Broglie hypothesis applies to all microscopic particles, not just electrons. An application of wave-like behavior of microscopic particles is the use of electron diffraction and neutron refraction to obtain molecular structures. Wavelength of a charged particle can be derived following the Broglies relation. If a charged particle, that is an electron of mass m and with charge q, is accelerated through a potential difference of capital V so as to acquire a velocity small v, then we can write lambda equals h by square root of 2q capital V into m. The Broglie wavelength of a proton or an alpha particle can be derived using the same expression. We will see this in the examples at the end of this discussion. A number of wavelength and energy relations can be derived from the Broglie wavelength. We will see this one by one. Wavelength of particles, that is neutron or gas molecule etc., can be derived by incorporating kinetic energy capital E. The number one relation is E equals P square by 2m. Secondly, lambda equals h by square root of 2 into E into m. Thirdly, lambda equals h by square root of 2 into total energy minus potential into m. The third equation above shows that the wavelength of a particle with constant energy E will change as it moves into a region with different potential energies. Thus, as an electron with constant energy moves into a region where it has a higher potential energy capital V, its energy decreases and its associated wavelength increases. In the fourth relation, we will see how the wavelength of a gas molecule changes with temperature. The relation is lambda equals h by square root of 3m kb into T, where kb is the Boltzmann constant. Now the question that surely comes in our mind is, does wave-particle duality really work? The answer of this question will be like this: electrons show particle-like behavior in some experiments and wave-like behavior in others. A similar situation holds for light also. Although both electrons and light exhibit an apparent wave-particle duality, there are significant differences between these entities. Electrons always travel at speeds less than c and have a non-zero rest mass, while light travels at a speed c in vacuum and photons have zero rest mass. Actually, wave and particle models are incompatible to each other. An entity cannot be both a wave and a particle. Then how can we explain the apparently contradictory behavior of electrons? The source of this difficulty is the attempt to describe microscopic entities like electrons by using concepts developed from our experience in the macroscopic world. The particle and wave concepts are developed from observations on large-scale objects, and there is no guarantee that they will be fully applicable on the microscopic scale. Under certain experimental conditions, an electron behaves like a particle. Under other conditions, it behaves like a wave. According to the Broglie, the nature of an electron moving around the nucleus is like a wave, and that follows in circular orbits around the nucleus. However, an electron is neither a particle nor a wave. In new theory, electrons in an atom are visualized as diffuse clouds surrounding the nucleus. The idea that the electrons in an atom move in definite orbits, that is in Bohr's model, is now abandoned. The new theory assigns definite energy states to an atom but discards a definite path for moving of an electron. Now we will see how the Bohr's postulate and the Broglie hypothesis can be correlated. One of the postulates of Bohr theory is that angular momentum of an electron is an integral multiple of h by 2 pi. This postulate can be derived with the help of the Broglie's concept of wave nature of electron. Consider an electron moving in a circular orbit around the nucleus. By assuming that the electron exhibits wave-like properties, only those circular orbits for which the circumference, that is 2 pi r, is equal to an integral multiple of the wavelength, that is n lambda, will form a standing wave as shown in figure 1. Now we will see how that the Broglie's ideas interprets the Bohr's orbit. This assumption means that the wave repeats itself with the same phase, that is with crests in same positions, on trip around the orbit as depicted in figure 2a, 3a and 4a. The situations depicted in the figures 2b, 2c, 2d, 3b and 4b are assumed not to occur. Now we will calculate the angular momentum in Bohr's orbit. This implies the circumference of Bohr orbit must be equal to an integral multiple of wavelength lambda, that is 2 pi r equals n into lambda, where n is called principal quantum number, is an integer. From this expression we can get the value of lambda, that is 2 pi r by n, where r is the radii of the orbit. Now from the Broglie equation we get lambda equal to h by mv, or we can write 2 pi r by n equals h by mv. From this expression we can get the value of angular momentum, that is nh by 2 pi. The above expression is the Bohr's postulate of angular momentum, where v is the velocity of electron and n is the principal quantum number. Thus, the number of waves an electron makes in a particular Bohr orbit in one complete revolution is equal to the principal quantum number of the orbit. This proves that the Bohr and the Broglie concepts are in perfect agreement with each other. Further developments after the Broglie's hypothesis. This confirmation of the Broglie's prediction brought duality into the concept of the nature of fundamental particles. A particle was not simply a particle but had a wave aspect to its nature. This idea led very quickly to the development of wave mechanics or quantum mechanics by Heisenberg and Schrödinger. All of our modern ideas on atomic and molecular structure are based on wave mechanics. The Davison and Gamma experiment was critical in the development of quantum mechanics in that it showed that particles exhibit wave behavior. If this is the case, there must be a wave equation that relates the spatial and time dependencies of the wave amplitude for the wave-like particle. This equation could be used to describe an atomic scale system rather than Newton's second law, that is force equal to mass into acceleration. It was Owen Schrödinger who formulated this wave equation, which will be discussed in the respective lectures. Now we will do some problems that will help you to acquire a solid hold on this topic. Example number 1. What is the Broglie wavelength lambda of an electron moving with a speed nearly 1/10 of light, that is 3 multiplied by 10 to the power 7 meter per second. Putting the respective values in lambda equals h by mv, we get 2.425 into 10 to the power minus 11 meter, that is actually 0.2425 Armstrong. Thus, an electron or any other object of the micro world, the wavelength falls within the dimensions of the atomic system to which the electron belongs. Problem number 2. What is the Broglie wavelength of a proton traveling with 1% speed of light? Similar to the last problem, the Broglie wavelength lambda is calculated as 1.32 into 10 to the power minus 13 meter, that is 0.20132 Armstrong. Problem number 3. What is the Broglie wavelength of an alpha particle emitted from a nucleus with a speed nearly 1/100th of speed of light? Like the previous problems, we can calculate the wavelength of the alpha particle as 3.316 into 10 to the power minus 14 meter. Here one point to be noted that if a nucleus of mass capital M at rest emits an alpha particle of mass small m, the Broglie wavelengths of the alpha particle and the residual nucleus will be in the ratio of 1:1. The nucleus is initially at rest. By the conservation of momentum, we can assume that the momenta of the alpha particle of mass small m and the residual nucleus will be equal and opposite. The Broglie wavelength is inversely proportional to momentum. Hence, the Broglie wavelengths of the alpha particle and the residual nucleus will be in the ratio equals 1:1. Next problem. What is the Broglie wavelength of a hydrogen atom moving with a velocity of 2000 meter per second, given that atomic mass of hydrogen equals 1.20797 AMU? First, we have to calculate the mass of hydrogen atom in kg. How we will calculate? We will divide 1.20797 with 6.023 into 10 to the power 23 into 10 to the power 3, that will come 1.67 into 10 to the power minus 27 kg. Then we will easily calculate the lambda from the equation lambda equal to h by mv, that comes around 1.98 into 10 to the power minus 10 meter, that is 1.98 Armstrong. In the next problem, we have to calculate the Broglie wavelength of a rifle bullet of mass 2 into 10 to the power minus 3 kgs moving with a speed of 300 meter per second. From the relation lambda equals h by mv, we can calculate the wavelength of the bullet equals 1.1 into 10 to the power minus 33 meters, that is 1.1 into 10 to the power minus 23 Armstrong. Yeah, that's an interesting result. We find that the wavelength of a rifle bullet or any object of the macro world, such as a tennis ball or a racing car, is negligibly small, and the wave nature would come out to be very much insignificant in comparison to the particle nature of the object. Problem number 6. What is the Broglie wavelength of an electron that has been accelerated through a potential difference of 100 volts? Here first we have to calculate the energy of the electron in electron volt. How we will calculate? We will multiply 1.602 into 10 to the power minus 19 coulomb with 100 volts, that comes around 1.602 into 10 to the power minus 17 joule. Now we will calculate that the Broglie wavelength from the equation lambda equals h by square root of 2 em. The value comes around 1.226 into 10 to the power minus 10 meter, that is 0.1226 nanometer. The example number 7 is little different. In part A, we have to find out the speed of a neutron such that the Broglie wavelength is 1.5 into 10 to the power minus 10 meter. In part B, we have to calculate the temperature such that the root mean square speed of the thermally equilibrated neutron is equal to the speed what we obtain from part A. How to solve this problem? In part A, we have to calculate the velocity of the neutron from the equation V equals h by m lambda. Putting the values, we get 2.645 into 10 to the power 3 meter per second. That is the velocity of the neutron. Now part B. Here first we have to calculate the root mean square velocity. From kinetic theory, we know the Vrms equals square root of 3 kBt divided by m, which should equal to 2.645 into 10 to the power 3 meter per second, which we obtained from the part A. After rearranging, we get the value of temperature, that is m Vrms square divided by 3 kb. After putting values, we get the result, that is 282 Kelvin. Problem number 8. Two particles x and y are in motion. If the wavelength associated with particle x is 4 into 10 to the power minus 8 meter, calculate wavelength associated with particle y if its momentum is half of x. How we will do this sum? Lambda x equals h by px and lambda y equals h by py. If we find the ratio of lambda x is to lambda y, which will be equal to py divided by px. Now putting the value of py, that is half into px, lambda y equals 2 into lambda x, that will come around 8 into 10 to the power minus 8 meter, which is the lambda associated with particle y. Next, it is given that the threshold wavelength of a metal is lambda 0. Find that the Broglie wavelength of photoelectron when the metal is irradiated with the radiation of wavelength lambda. We know absorbed energy equal to threshold energy plus kinetic energy of the photoelectron. That is h nu equals h nu 0 plus E. After rearranging and putting the value of nu, we get hc by lambda equals hc by lambda 0 plus E. From this equation, we will get the value of energy, that is hc into 1 by lambda minus 1 by lambda 0. If we put the value of kinetic energy into the Broglie equation, that is lambda equals h by square root of 2 em, we will get square root of h into lambda 0 divided by 2 into mc into lambda 0 minus lambda. In the next problem, we have to calculate the typical wavelength of neutrons after reaching thermal equilibrium with their surroundings at 373 Kelvin, assuming that the particles are traveling in one dimension. We know the kinetic energy of a neutron E equals p square by 2m. From equipartition theory, the kinetic energy at thermal equilibrium in x direction, that is E equals half into kBt. Therefore, p square by 2m equals half kBt, or we can write p equals square root of m kBt. After putting the momentum in the Broglie equation, we will get lambda equals h by square root of m kBt. After putting all the values, the result is 2.26 into 10 to the power minus 10 meter. Example number 11, part A. Obtain that the Broglie wavelength of a neutron of kinetic energy 150 electron volt. Would a neutron beam of the same energy be equally suitable for crystal diffraction experiments? Part B. obtained the Broglie wavelength associated with thermal neutrons at room temperature 27 degrees Celsius. Hence, explained why a first neutron beam needs to be thermalized with environment before it can be used for neutron diffraction experiments. In part A, first we have to calculate the energy of neutron. That will equal to 2.4 into 10 to the power minus 17 joule. Now putting the value of energy of the neutron in the Broglie relation, we get 2.336 into 10 to the power minus 12 meters. Hence, we can conclude that the neutron beam of 150 electron volt of energy is not suitable for crystal diffraction experiment as the lambda smaller than interatomic scale. In part B, we will calculate the wavelength of thermally equilibrated neutron from the equation lambda equals h by square root of 3m kBt. Now put the values. In the numerator, 6.626 into 10 to the power minus 34 divided by square root of 3 into 1.675 into 10 to the power minus 27 into 1.38 into 10 to the power minus 23 into 300. The value comes as 1.453 into 10 to the power minus 10 meter, that is 1.453 Armstrong. Thus, the wavelength is comparable to the interatomic spacing of a crystal. Hence, the high energy neutron beam should first be thermalized before using it for diffraction. Example number 12. Electrons are used to determine the structure of crystal surfaces. To have diffraction, the wavelength lambda of the electron should be in the order of the lattice constant, which is typically 0.30 nanometer. What energy do such electrons have? Find answers in electron volts and joules. We know the kinetic energy of an electron E equals p square by 2m equals h square by 2m lambda square. After putting all the values, we get 2.7 into 10 to the power minus 18 joule, that is 17 electron volts. It is given that a proton has kinetic energy E equals 100 kilo electron volt, which is equal to energy of a photon. Let lambda 1 to be the Broglie wavelength of the proton and lambda 2 be the wavelength of the photon. We have to correlate the ratio lambda 2 by lambda 1 with the energy. How to do this? Firstly, we have to write the wavelength of proton, that is lambda 1 equals h by square root of 2em, and same for the photon, lambda 2 equals hc by e. Now write down the ratio lambda 2 is to lambda 1 equals c square root of 2m divided by square root of e. As c square root of 2m is a constant, we can write the ratio lambda 2 is to lambda 1 is proportional to e to the power minus half. Example number 14. An electron with speed v and a photon with speed c have the same Broglie wavelength. If kinetic energy and momentum of electron is E electron and P electron and the photon is E photon and P photon respectively, then find the correct answer. For photon, we can write E photon equals mass of photon multiplied by c square. For electron, we can write energy of electron equal to half into mass of electron into v square. At the same time, it is given that the Broglie wavelengths of the electron and the photon are same. From this expression, we will get the mass of electron divided by mass of photon equals c divided by v. If we put the ratio in energy of electron divided by energy of photon, after rearranging, we get v divided by 2c. So the correct answer is answer B. Question number 15. Is the wavelength of electron in different orbits same or different? If different, What is the ratio of the wavelength in first and third orbit? Wavelength of electron in the first orbit equals lambda 1 equals h by m v1. In third orbit, lambda 3 equals h by m v3. Therefore, lambda 1 by lambda 3 equals h by m v1 divided by h by m v3, that is equal to v3 by v1. Also, in Bohr's orbit, Vn equals E square divided by 2 epsilon 0 nh. For V1, E square divided by 2 into epsilon 0 into h, and V3 E square divided by 2 into epsilon 0 3h. Therefore, V1 by V3 equal to E square by 2 epsilon 0 h whole divided by E square divided by 2 epsilon 0 3h equals 3:1. Therefore, lambda 1 divided by lambda 3 equal to V3 by V1 equals 1:3. Problem number 16. Find that the Broglie wavelength associated with a photoelectron that varies with the frequency nu of the incident radiation. Consider nu0 is the threshold frequency. We know absorbed energy equals threshold energy plus kinetic energy of photoelectron. Therefore, h nu equals h nu0 plus E, or h nu0 plus half mv square. After rearranging, we get V equals square root of 2h nu minus nu0 divided by m. If we put the value of V into the Broglies relation, we get lambda equals h by mv equals square root of h by m into nu minus nu0. Question number 17. Determine that the Broglie wavelength lambda and the velocity v associated with an electron emitted by a metal whose threshold frequency is 2.25 into 10 to the power 14 Hz when exposed to visible radiation of wavelength 5 into 10 to the power minus 7 meter. From photoelectric effect, we know absorbed energy equals work function, that is the threshold energy plus kinetic energy. Therefore, we can write h nu equals work function plus half mv square. We will denote the work function as phi. Therefore, we can write phi equals h nu0. After putting the values of h and nu0, we will get the value of work function, that will be equal to 1.49 into 10 to the power minus 19 joule. Now we will find the value of h nu, that equals h c by lambda. After putting all the values of h, c and lambda, we get h nu equals 3.98 into 10 to the power minus 19 joule. After subtracting work function from h nu, we get the value of energy, that is equal to 2.48 into 10 to the power minus 19 joule. Putting the value of energy in the Broglie relation, we get the wavelength equals 9.84 into 10 to the power minus 10 meter, that is 9.84 Armstrong. Now come to the second part of this question, where we have to find out the velocity of associated electron. We know E equals half mv square. After rearranging, we get V equals square root of 2e divided by m. After putting all these values, we get the velocity V equals 7.39 into 10 to the power 5 meter per second. Example number 18. Find the kinetic energy of the electron when an electron and a proton have the same Broglie wavelength lambda. We can write lambda E equals h divided by square root of 2 energy of electron multiplied by mass of electron. Similarly, for proton, lambda p equals h divided by square root of 2 multiplied by energy of proton multiplied by mass of proton. As lambda E equals lambda p, therefore energy of electron multiplied by mass of electron equals energy of proton into mass of proton. After rearranging, we get energy of electron equals mass of proton divided by mass of electron into energy of proton. Therefore, we can write energy of electron is greater than energy of proton, as mass of proton is greater than mass of electron. Therefore, the correct answer is answer D. Problem number 19. An electron and a photon have the same Broglie wavelength lambda. If P is the momentum of electron and E is the energy of photon, find the magnitude of P by E in SI unit. We know for electron P equal to h by lambda, for photon E equals h nu equals hc by lambda. Therefore, we can write P by E equals 1 by C equals 1 by 3 into 10 to the power 8 meter per second, and the value comes around 3.33 into 10 to the power minus 9 second per meter. Example number 20. What is the Broglie wavelength of a nitrogen molecule in air at 300 Kelvin, assuming the molecule is moving with the root mean square velocity of molecules at this temperature? Given that atomic mass of nitrogen equal to 14.2076 U, the mass of a nitrogen molecule equals 2 into 14.2076 divided by 6.023 into 10 to the power 23 into 10 to the power 3 kg, that is equal to 4.65 into 10 to the power minus 26 kg. If we put this value into the Broglies relation, we get lambda equals h by square root of 3m kBt equal to 0.275 into 10 to the power minus 10 meter. So this is all about the Broglie hypothesis. I hope everything is very clear to you now. For any queries about this topic, you can always chat with me on WhatsApp at 983191245. Thank you for attending my lecture. In the following class, we will meet with another interesting topic. Till then, thank you and goodbye.